Bismillahir Rahmanir Rahim. Path vector routing. We have seen distance vector routing and we have seen link state routing. In both cases, the goal was to find the least cost. We were looking to find the least cost between the nodes. However, many times, this is not the goal. This is not the priority. It is very much possible that we want to choose something else as the metric or the goal. For example, maybe we would like to choose the path that has the most security. So this option is not available to us in least cost routing. Okay? So if we have, for instance, we could have nodes where the path A, D, E is the least cost. However, A, B, E is more secure. Okay? So this path has more security, and this is what we want. Okay? With least cost routing, you can't make these choices. You can't choose what your metric is, what policy you want to apply. But in path vector routing, you can choose it. So you could have every node in here having its own policy. And every node will make its own unique spanning tree. In this case, we want to have security as the priority. And because we're using path vector routing, we can make a spanning tree in which we avoid the route A, D, E, and we take the route A, B, E instead. And this is necessary because sometimes we don't want our network packets to go into someone else's networks, like rival networks, or we could have for example, geographical boundaries. We don't want to have the packets of a certain region entering the packets of another region for security reasons. We don't want people to hack or to capture our, not hack, but to capture our packets and to read the information inside. So if we know that a certain way is more secure, we will choose that, even though it may not be the least cost in some other sense. So this is why we make use of path vector routing. So we can specify different policies to route the packet. In this case, we have a network of 5 nodes, A, B, C, D, and E. Now this is A's spanning tree. A's spanning tree has been made in such a way that we are avoiding D to be an intermediate node. We are avoiding the information to flow from D, to flow through D. We are avoiding that. Similarly, in B's spanning tree, we are avoiding the information from flowing through C. So all information to E will instead go through D. So in this way, every node has applied its own policy. In path vector, we could even have multiple spanning trees at a node based on different policies. Okay, so we could have one policy for security at A, let's say, okay? And for that, let's say this is the spanning tree. We could have a policy for delay, less delay, okay, less delay. And in this case, we could have a completely different spanning tree, okay? So in this way, we could even have every node having multiple spanning trees based on the policy that it uses. Now, how do we know the nodes? How do they come to know about this? Again, this is something similar. We have the distance vector. Every node, when it comes up, mind you, all these nodes don't come up at the same time. They will come up when they have to come up. Okay, they will come on when they have to come on, not at the same time. This is asynchronous. So when A comes on, it will look at the neighbor and it will make its spanning tree, its path vector, sorry. It will make the path vector, which in turn will contribute towards the spanning tree. And then you have B also doing the same thing. If we want to go to A, the route is B, A, B to B is B, B to C is, if you want to go to C, then it is BC. If you want to go D, it's BD. Okay? And similarly, each one of them has made its own path vector. In this case, we are assuming that all of them are using the same policy. Now, updating the path vectors. We have the old path vector for C. The path vector for B has arrived. In this case, we now have a new entry, which is we now know how to go to A. So we take this route and we first add C to the beginning and then we put the route in. Okay, so this is how the route has come in. B, you know, there is an entry for all these other values, so it's not a problem. We don't really consider those, because remember, these are the neighbors, okay? And then we have E. E doesn't have anything here, so all the others will remain the same. So this is C receiving a copy of B's vector. Now we take this and place it here. Now C has received next the copy of D's vector. In this case, we have everything else remaining the same because we don't really have any other new information. So this is how we will implement path vector routing. Remember, in here, the policy can be other than cost. It's not the least cost we are considering here. We could be considering many different things based on the need of the network.